So the next few videos are about the comparison tests, and the first of the comparison tests is called the direct comparison test. And the test can be used to show that a series either converges or diverges. It's not like the nth term test for divergence that can only show divergence. It's a test that can potentially show either way, right? So there's sort of two cases, right? So first, if you want to show that a series that you have converges, right? So suppose you've got some series Cn and you want to show it converges, right? Well, suppose that you know about some series An that converges and has positive terms. If your series Cn, if every single term is less than the terms of An, for all values of n, then you will know your series Cn converges. Right? Now keep in mind, if Cn, the series that you have, is actually bigger than the terms of the convergent series, then we don't know anything about the convergence of Cn. So I know this is all fairly formal language. I'm going to go through a more sort of everyday English version of this in the next slide, right? But I do need to talk about how you also use it to show that a series can diverge, right? So suppose that you have some series Bn, and you know that Bn diverges. You know that these terms do not add up to something. As you try to add them to infinity, it gets larger and larger and larger, right? So you know that Bn diverges. If the series that you're trying to find out about, if Cn is bigger than Bn for every single term, well, if Bn diverged and Cn is even bigger than that, then Cn would have to diverge. Right? And again, as a note, if you know that Bn diverges and you know that C sub n is less than that, we really don't know anything about that. And we can't say whether Cn would converge or diverge in that case. Right? So this is the formal presentation of the language. Next, I'm going to sort of go into explaining what that means. Alright, so now I want to try and explain the direct comparison test sort of in plain English. And I have a version of it written here in English, but I actually want to tell you a story about a door, right? So let's say that there's, here's the ground and there's a doorway over here, right? And this doorway is like the doorway of convergence, right? And so the way it works is series will walk towards the doorway, right? And the idea is some series are really short, and so they'll walk through the doorway, right? Some series are really tall, and they'll smack their head on their way as they try and walk through the doorway. The idea is if a series is small enough, it can fit through the doorway of convergence, right? The series that are small enough will converge, right? But series that are too big will sort of try and walk through and will sort of hit their heads on the doorway of convergence, right? So the idea here is, let's say that you have some series here, C sub n, and you want to know if your series will converge. In other words, you want to know if your series is going to make it through the doorway, right? Well, imagine that you know some series A sub n that made it through the doorway. Like A sub n was short enough to make it through the doorway. And then you look at it and you're like, hey, wait a minute. I know that my series is always smaller than A sub n. Well, wait a minute. If your series is always smaller than A sub n, and A sub n was small enough to make it through the doorway, then guess what? C sub n is going to make it through the doorway, right? Now, let's sort of spin that the other way around, right? Suppose that you know that A sub n converges, and you're like, oh, C sub n is bigger than that. It'll definitely hit its head. We actually don't know that. Like, if something's bigger than A sub n, it might hit its head, it might not. I don't really know, and I can't say that, right? So the idea here is, if you already know about some convergent series, An, and your series is less than that, then you know that yours will converge, right? We can talk about it in a very similar way for divergence. So again, imagine, here's the doorway of convergence. So you're sitting there minding your own business, and you see this series A sub n, and A sub n walks along and hits its head on the doorway of convergence, right? If you know that your series C sub n is always bigger than that one, there is no way that C sub n is going to make it through the doorway, right? But what if C sub n was less than A sub n? Can you tell me whether that converges or diverges? We can't. Like, I know A sub n was too tall, but if something is shorter, it might still hit its head, or it might make it through. That's sort of the plain English sense, with my crazy doorway take on what the direct comparison test does. Alright, so how do we actually use this test? So the direct comparison test relies heavily on you having like a mental library of series that converge and diverge. In other words, you need sort of at the drop of a hat to be able to know lots of things that converge and diverge. And so fortunately we've got some things like that. Like specifically p-series and geometric series are huge. Like you guys all sort of liked in class how easy p-series were, and when you get the hang of it, how easy geometric series are. Even the integral tests, like we sort of get used to seeing these ones. And the idea is what we're going to do is we're going to take more complicated series and say, you know, these series sort of look like some of these other things, and we can compare them to a p-series or a geometric series or an integral test type series and show that our more complicated series converge. So I've got a few examples, and we need to get to those because I know this video is already on the long side. So here's my first example, right? I want to use the direct comparison test to show that this series converges, right? So what I need to do is I need to come up with some other series that converges. So I need to find a series that converges that this series is actually smaller than. And so what we hopefully notice is that, you know, this series over here, the one that you were given, it has an n squared on the bottom. Like, that should feel a little bit like a p-series, right? So maybe we could compare it to the series 3 over n squared. This is a convergent p-series, right? We know that series converges. We know that, like, right off the top of our heads. We don't have to think about it. We can see that this is a p-series with a p-value being 2. 2 is bigger than 1. It automatically converges. So then the only question is 3 over n squared plus 5, is this always less than 3 over n squared? We know that this one converges. We know this one fits through the doorway. So if I can just show that this one is shorter than that one is, we're golden. We're set by the direct comparison test. Right? And the idea is, you can tell that this series is in fact smaller than the p-series is. The reason is that the denominator is actually larger in this one, and if we increase the size of the denominator, it's definitely going to be smaller than this other thing is, right? So how do we write about this, right? Well, we might say something like, since 3 over n squared plus 5 is less than 3 over n squared for all n greater than or equal to 1, and by the way, I got this from like where this series starts. If this series starts at 1, then it needs to be true for all n greater than that value. So since that's true, since that is less than that, and we might say, and the series 3 over n squared converges as a p-series, then we can say the sum of 3 over n squared plus 5 converges by the direct comparison test. Sorry for my horrible handwriting there, but I wanted to get through it quickly. This type of writing is what I want to see for effectively every one of these problems. Like, we need to write out in a sentence or two in explicit detail, why is this test working? Why are you using it? What causes it to work? Alright, so this time I want us to use the direct comparison test to show that this series actually diverges. Right? So pause the video, see if you can sort of think of a series that this is related to that you could use the direct comparison test with. So the idea this time is that we need to know about a series that diverges, which this series is greater than. Okay? So my sense is that we should use the series 1 over n. This is a divergent p-series. It's actually the harmonic series, which is, you know, a p-series for p equaling 1. And the idea here is we can say conclusively that the natural log of n over n is greater than 1 over n for all n greater than or equal to, I suppose it's actually not greater than or equal to 1 that we have to say. I think it's actually only for n greater than or equal to 3. But that's actually okay with the direct comparison test, as long as there's some point beyond which the series that you're looking at is always bigger than the one that you're comparing to, you're good to go. The reason this is true, by the way, is that as n gets larger and larger and larger, the natural log of n gets larger and larger and larger, whereas 1 sort of just stays 1. Right? So because of this, you know, because the natural log of n over n is greater than n, we know that the sum of the natural log of n over n diverges whoops, this should have been 1 over n, diverges by the direct comparison test, right? It's better for us to write out direct comparison test. If you're in a hurry, you can get away with DCT. I wouldn't recommend doing it on the IB exam or the AP exam, but for sort of informal things for the homework, we can live with it. Last example. Use the direct comparison test to determine if the series below converges or diverges. In the last two examples, we had a very easy comparison. Like, we were able to very easily see, like, oh, yeah, I can see what this thing is connected to. 1 over n factorial is actually a little bit more difficult. So this is an example where I like to sort of show people sometimes when you're working with a series, sometimes it helps a lot to write down the first few terms just to get a feel for the series, to get a feel for whether we think this thing converges or diverges, so that we know how to compare it. And in this case, I don't really know what to do. So what I'm going to do is I'm going to just write out the first several terms. My first term would be 1 over 1. My next term would be 1 over 2, that's 2 factorial. The next would be 1 over 3 factorial, which is 6. The next would be 1 over 4 factorial, which would be 24. I mean, the next one after that would actually be 1 over 5 factorial, which is 120. And so the idea we have here is, wow, this series is getting small very, very fast, which makes me think this probably converges. So if I can find a convergent series, which this is always smaller than, then I'll be in good shape, right? So I'm going to try a p-series. I'm going to try the series 1 over n squared. 1 over n squared would give me 1 over 1, 1 over 4, 1 over 9, 1 over 16, 1 over 25, and I could sort of keep going here. So the question is this, are all the ones on the left, are these actually smaller than the ones that are on the right? And after a point, we can see the answer is yes. Like way down here at the bottom, 120th is definitely smaller than 125th. The next one down, and the next one in the factorial chain, we could even write it down, 1 over 720, that's like way smaller than 1 over 36, right? The troubling part is all this stuff in the beginning, right? Like in the beginning, the ones on this side are actually larger than these ones are, and there are sort of two ways to answer this. One is to say, I did mention to you guys, as long as there is some point beyond which it's true, you're fine, right? Because the idea is these things will add up to something, and then all of the stuff over here is going to be really small, so it'll certainly allow you to add up. The other thing that you can do on these is you can actually be a little bit sneaky. Instead of doing 1 over n squared, just make it 10 over n squared. Because if I made it 10 over n squared, this first term would be 10, which is way bigger than this. This next would be 10 over 4, which is way bigger than this. The next would be 10 over 9, which is way bigger than this. The next would be 10 over 16, which is way bigger than this. And from that point on, we were doing fine anyway. From that point on, this side was totally small enough to win regardless. So this is a very strange application of the direct comparison test, but I wanted to give you exposure to one where it wasn't super clear, and we had to write down several terms and compare them. If there's something about this that seems fishy to you, or if you don't get it, please write down that question. I know that this is a strange test to wrap your mind around, and I want to be able to answer your questions when we get to class.